will start with a little bit of history, who we are and what was the evolution from Celera, Elbit Energy, PO-Celltech today. So it all started in 2008. Elbit Systems, Land and C4I division at that year established the supercapacitor research and development program and group. And Celera was established in 2008 by Professor Shimshon Gottesfeld and Dario and Ziv Gottesfeld. In January, actually it was in December 2014, Elbit Systems bought the assets of Celera, and we become a joint group, moving from the corporate of the Land and C4I division from Netanya to Caesarea. And in July 2016, a joint venture was established between Elbit Systems and Plastic Omnium, and our company, PO-Celltech, was created with the mission profile to research and develop energy storage and conversion devices for automotive market. So, in a glance, we have two fields of activity: alkaline membrane fuel cell and hybrid alkaline supercapacitors. We are 40 employees. 30% of those are with PhDs in the electrochemistry, nanotechnology, and material science and engineering. We are blessed to be backed by two huge companies, one large electronic defense company, Elbit Systems, the largest private one in Israel and among the top 30 companies in the world, and Plastic Omnium, a very large tier 1 supplier in the expertising in exterior components and fuel systems. As I mentioned, we are an R&D-oriented company. We conduct plenty of research covering from the material state up to the more systematic approach and systematic devices, with the core competencies being focused on the materials for either electrodes for supercaps or novel catalytic materials for the catalytic layer of our alkaline membrane fuel cells, electrolytes for supercaps, ionomers for alkaline membrane fuel cell, separators and membranes, and both structural and plastic and polymeric or plastic components for the outer part of the devices. We have simulation and modeling capabilities in terms of lifetime prediction and thermal analysis and mechanical analysis design, and also the compatibility of these devices to a variety of transportation profiles, while in terms of system integration and their implementation in the electromobility, this is support that actually we take from our large matrices, either Elbit or Plastic Omnium. So, and of course, all this research is not done only by ourselves, even though we have a very extensive research team in-house, but we don't do it all by ourselves. So we work very strongly in the field of alkaline exchange membrane fuel cells with all the universities in Israel, most of the universities in Israel, as well as with international academic group. In terms of the electrocatalysts, we work with Professor David Zaitoun at Bar Ilan University. We work with Professor Morris Eisen for developing advanced ionomers, which are stable at high temperatures. We worked with Professor Simon Brandon and did some 2D and 3D modeling of our AMFC. We worked with Professor Yoed Sur to develop some impedance spectroscopy analysis on AMFC. In terms of the international collaboration, we work with ZSW in Germany for our AMFC stack design, and with a variety of institutions in US like Brookhaven, RPI, and UDEL for covering mainly the ionomers, the catalyst, and of course the ARPA-E for a direct ammonia fuel cell project. Okay, this is something that a colleague of mine kindly took a picture in Paris and sent this to us, showing the fuel cell taxi fleet in the downtown part of Paris. You here see the Hyundai fuel cell vehicle. In both sides, you have the Clarity and the Toyota Mirai. So actually, the automotive fuel cells are today a reality. And the question is whether they will ever be a mass market technology. And we know that our formula for a zero emission transportation success of such a device should be, first of all, the same price as the ICE vehicle, the same user experience, and actually this will give us the solution of a mass market success. In terms of the technology point of view, the fuel cell has the technological competitiveness to become, to give the same driver experience in terms of the power, in terms of the range, in terms of the fast charge. What is lacking there is the infrastructure, and here, in order to speed up this process, a lot of, the governmental support, either via regulations or incentives or penalties, is very much required. So the current automotive fuel cell technology is the PEM, and I don't want to go into much more details into that, because we all know that this is the current choice for the automotive fuel cell, hydrogen fuel cell technology, following those characteristics of high power density, the fast startup charge, the capability to be started up even at lower temperatures. And the question is whether this can be truly mass market success, and the main challenge there is the high cost. And here I have taken the liberty to put some slides from Dimitrios and from the AMR in October 2016 meeting. And here you can see that the high costs are mainly due to the materials and base components, like the platinum-based electrodes and the expensive bipolar plates. So this is, again, a DOE data. Actually, this is not the latest one. It's from 2015. And you can see that these DOE costs projections have been based on this 80 kilowatt net for a PEM fuel cell system, taking under the consideration that we are talking about a mass production, 500,000 units per year. And you can see that the ultimate target of $30 per kilowatt is still, there is still a lot of work until this target can be met. When we look at our alkaline membrane fuel cell technology, and Dario explained previously, it has the potential to become an enabler for actually promoting the penetration of the fuel cells in the automotive market and reducing the cost, basically due to those basic components and materials that actually are today very costly for the PEM, like the membrane, the non-platinum catalyst, and the low-cost metal hardware. So, but we talk about low cost, but actually there is no low cost without having achieved the high power density. So when you look again at those DOE projections, then you see that 45% of the stack cost is being by manufacturing and other materials. So all the components actually scale up in a linear mode with the aerial power density. Therefore, one main condition for alkaline exchange membrane fuel cell to be there in the automotive market is, first of all, to approach or equalize the PEM power density. And okay, here truly I don't want to go into details about the challenges that we had to go over in order to speak today about alkaline exchange membrane technology. These were covered. But what I would like to show is that a year ago, in 2016, we with our low PT anode catalytic layer were at this. What is that? Actually, we're at this area on the. We're at the red curve in the graph over there, with our 30 micron membrane and loading of low than 0.1 milligram PGM per square centimeter. And the black curve over there shows where PEM best low PGM scenario of lower than 0.15 milligram per square centimeter was at 2016. So you can see the large gap over there that we had to deal with in order to be able to say that we can be a substitute for PEM in terms of the power density at beginning of life. And actually, our important win this year at PO-Cell was the fact that we managed with PGM loading of lower than 0.1 milligram per square centimeter, we are talking about 0.05, if I remember correctly, to actually meet the performance of the state-of-the-art according to DOE PEM IV curve. So actually, we also believe that we are just in the beginning, so there is a lot of room for further improvements, and this is one of our main focuses. Going into the, having said that and putting these projections in terms of the cost, we and all the community actually asks where can we be with the alkaline membrane fuel cell technology. So when you look at the DOE projections and the DOE targets and projections, you can see that the time curve for PEM does not converge to those targets in a reasonable time frame. So if we want to get closer to those $30 per kilowatt, which will make the fuel cell vehicle a substitute for an ICE vehicle, we have to go and find alternatives for bringing the cost down. And the alkaline exchange membrane fuel cell, looking at those cost projections, seems like a capable solution for putting the fuel cell vehicle in a place that it can be cheaper than a battery vehicle for sure, and maybe even cheaper than an ICE vehicle, but at least close to an ICE vehicle. What is the challenge? The challenge is the durability, and the durability of our alkaline fuel cell has been and is still being the main target that we actually, today that we have the beginning of life performance, try to tackle to in order to make this technology mature and compatible. So what we did, and that is a challenge as well, because the community has been working for more than 2 or 3 decades on PEM, but not so much on the alkaline exchange membrane fuel cell. As you heard, it was a pioneering, let's say, pioneering activity that started 10 years ago only, and now the community is much more into that. But nevertheless, we have a gap to fill in terms of the expertise. So, of course, in order to properly evaluate the durability in those automotive conditions, we had to design a drive cycle template. And as there are no acceleration or stress test procedures there for alkaline exchange membrane fuel cell, then we looked at the DOE PEM fuel cell testing protocols and try to adapt those to ours. So this is the protocol that actually we took under the consideration and started to test our fuel cells. You can see that what you can see there is the power level, the time, and the current density specifically. And these are the results. So when you look at the durability data of our current state-of-the-art AMFC, at constant discharge setting, you can see that projected, this is where we were. Maybe I'll try to manage this one. This is where we were in 2015 status. This is the status in 2015. This is our current status, our actual status today, and if you look at the dotted line over here, these are the projected, this is the projected behavior, so you can see that if we use 15% of our power setting, and the projected lifetime can reach 2,000 cycles, at 30% of power, which actually discovers more than 50% of the overall drive cycle discharge time, we are at 1,200 hours. At 75% of power, we are at 800 hours. So the stack performance, though, at 100% power, it needs improvement, and actually the difficulties that result into this challenging durability come from the water management and the combination of the water management and the membrane. So going into that was, I would like also to mention here that besides of our low PT or low PT anode, which gives us the capability to state that we are a low PGM, lower than 0.1 milligram per square centimeter route, we have another route which we are investigating and have been investigating for over 4 years now with Professor David Zaitoun at Bar Ilan University, trying to go for a palladium nickel, and you saw this picture before. This work, by the way, I would like to acknowledge the support of the TEPS consortium. It's a national consortium, which actually is being funded by the Innovation Authority in Israel, what used to be the Chief Scientist Office. And this consortium deals with a variety of power and energy sources for electrical transportation. We worked and we continue to work with David on the low PGM route, and what we see here, what you see here, these are the targets or the years of the consortium. We just are in the end of our 4-year. And this is where we were in the third quarter of the 2017. And this is where we are now at the fourth quarter or at the end of 2017 year of TEPS consortium. So we are very close to reaching the 0.6 watt per square centimeter with a low PGM cathode. You can see that still there is a lot of sensitivity to the nickel-palladium ratio, and this is something that we have to deal with. And the next focus will be to further reduce the palladium loading of such an anode. And with this, I would like to finish and to say thank you and acknowledge the beautiful work that has been done by both R&D and engineering team. We would not have been here today without the brilliant mind of Dr. Miles Page. He's somewhere there. And all the R&D and engineering people who are working at PO-Celltech. And of course, it goes without saying, Professor Shimshon Gottesfeld, who is not only our super consultant, this is how we call him, but it is also a mentor for all these young and talented people there. And I would like to thank you all for your kind attention.